This is our second part of the application of integration. You remember in our previous video we talked about the area between two curves. We looked at the upper curve and the lower curve, and we said we could subtract the area between the curves. We also talked about the area below a curve and up to the x-axis, so between the x-axis and the curve. The question becomes what about the area below the x-axis? What happens if I have a curve that falls below the x-axis? What do I actually do with this? Well, what happens is when you do an integral, and you can do an integration of a curve that falls below the x-axis, but when you do this, what happens is you get a negative area. Well, that's not necessarily a bad thing. We just need to take into account for that, because if I ask you to find the total area between -1 and 1 for the function, between the x-axis and this curve, what would happen is you would actually wind up getting 0, because this is a odd function, so it's symmetrical with respect to the origin, so these two areas are actually equal. However, this area here on your left will give you a negative area, and this area here on your right will give you a positive area. So we need to find ways to account for this. Now some of you are thinking, well, why don't we just take this one on the right and double it, and that would actually work in this case because the curve is symmetrical. It may not work in every case because the curves may not be symmetrical. So how do we account for it when we don't know if the curve is symmetrical? There's some simple procedures. First, we want to split up the integral into a sum of integrals. Instead of integrating straight from -1 to 1, we want to split up the negative area and the positive area into two different integrals. And then we want to account for the actual negative area. The way we're going to do this is, instead of integrating from -1 to 1, to find the total area, we're first going to integrate from -1 to 0 to account for this piece, and then from 0 to 1 to account for this piece. The piece that we know is positive, we're just going to leave alone, and we're going to integrate that function with respect to x and not change anything. The piece that we know is negative, what we're going to do is actually put a negative in front of the function. In other words, we're going to account for the fact we already know the area is going to come up negative. So if we hit it with another negative, that's going to wind up being positive and counteract the negative area. Therefore, if I take a negative of a negative, that's a positive. So this gives me a positive area with this integral and a positive area with that integral. The last application we want to talk about is the future value of an investment. To date, we've calculated the future value of a one-time investment. We remember the equation A equals PE to the RT, where we invested a principal amount and just simply let it sit there over time. Well, what happens if we don't want to just let the money sit? What happens if we want to continue to make deposits? That's the way most investments work. Your IRAs, your 401ks, you're putting monthly amounts in or yearly amounts in. So to do that, this equation is simply insufficient. We need a new equation. So we're going to talk our last subject on a continuous income stream. Our definition: the future value of a continuous income stream of K dollars per year. So we're going to assume we're investing the same amount each year for n years at an interest rate R compounded continuously is this integral. Integral from 0 to n. So I'm starting at time 0 and going n years into the future. I'm investing K dollars per year, so the same amount, times E. R is my continuously compounded interest rate to the n minus t power, and I'm going to integrate this with respect to time. Let's see how this works. Find the future value in 5 years of an account that earns 8% interest and has $10,000 deposited in it each year. Here's my formula. My n in this case is 5. My K is 10,000. My R is 0.08. Again, my n is 5. And I'm going to leave this t alone because this is what I'm integrating with respect to. So I have the integral from 0 to 5 of 10,000 e to the 0.08 times 5 minus t, all in my exponent. Now when I go to integrate this, this isn't really that difficult because the 10,000 is going to come out. And I just have this exponential function, e to the 0.085 minus t. Well, we haven't really looked at things this complex yet, and really it isn't that complex in general, because if I distributed this, I'd get 0.4 minus 0.08t. And I remember when I integrated e to the kx, it was 1 over k e to the kx. Well, this is basically the same situation. My Constant I'm multiplying my variable by is actually negative 0.08. The 0.8 from out front, the negative from in front of the t, so I'm going to sit there and multiply by 1 over that constant, or just put it under the 10,000. So 10,000 comes down, negative 0.08 from the coefficient of t in here, and then the e function stays the same, e to the 0.08 times 5 minus t, and I'm going to evaluate this from 0 to 5. Now this becomes the standard integral for us when we have our evaluation. We need to evaluate first at 5, and then 0, and then take their difference. I'm going to leave this coefficient out front and not worry about it. I'm going to evaluate this at 5 and then at 0. When I evaluate this at 5, 5 minus 5 is simply 0. So anything to the 0, e to the 0 power is 1. And then I need to do this in my calculator. If you'll look, I have a lot of decimal places here. My suggestion is just to leave this in your calculator. Take this number, subtract 1 from it, and then multiply by 10,000 over 0.08. Notice I didn't say negative 0.08 because I flipped my subtraction here. I took this number, this was a positive number, I subtracted 1 from it. If you want to go ahead and make this negative and add 1, you're welcome to. And this is going to give you a value of $61,478.09. What this does, and the reason we need to use an integration, is because we are depositing every year another amount of $10,000. We're not just letting it sit.